It showed to me.
Ah, okay. Now
Okay.
it's recorded.
Yeah, I think
Okay.
Perfect. Okay. Well, thank you. Hello, everyone. So as Martina said, I'm going to talk about a part of my thesis that was focused on the creation of...
Oh,
We're good? Okay.
is it
So
now recorded?
yes, I have the little dot. I think it's recording. Yeah. Okay. So this part of my thesis was focused on the creation of a simple microphysics model that can be combined with observations from superpressure balloons in order to assess the impact of gravity waves on ice crystal populations in the tropical tropos layer. And this part of my thesis led to a paper that is now published in ACP. Oops. So, as you know, cirrus clouds are frequent, they impact Earth's relative budget, and they are key at the TTL where they regulate the amount of water vapor entering the stratosphere by the freezing drying process of the water vapor contained in the uplifted air parcels. Beyond their altitude and their thickness, it is really their microphysical characteristics that set their life cycle, their radiative properties, and their dehydration efficiency. Now it is commonly admitted that homogeneous nucleation is dominant in the formation of in situ cirrus clouds in the TTL, and thus that gravity waves, by generating high cooling rates, are key in the formation and the life cycle of these clouds. So we know that cirrus clouds are hard to represent and study as they gather a wide range of processes from planetary scale circulations to the microphysics of the nucleation of the ice crystals. And so all these processes can't be fully resolved in one model and choices have to be made. So here in our work, we know that we want to look at the effect of gravity waves on the ice crystals population and therefore the air parcel dehydration. And so to understand our strategy to achieve that goal, I'm starting by introducing some pre-existing models. So we know that Lagrangian box models are good to represent ice crystals population as well as ice density maxima, but they are limited regarding the air parcel dehydration and the representation of the cloud on a longer time scale than just the nucleation. Then, extended to the vertical, the curtain approach is good to track the size of the crystals in time and altitude, but it constrains artificially the air parcels to be horizontally aligned. And then we have bigger models that take into account the ice formation, growth, aggregation, sedimentation, and that can be linked to global climate models. But to assess the issue of the impact of small-scale dynamics on the macrophysics, we still need very precise information regarding the temperature variability generated. And so that led to the use of superpressure balloon observations for the gravity waves, for example, by Dean et al. In 2016, who used a box model to look at the effect of these waves on ice formation right at the nucleation. So what we did here is to extend this model by adding a vertical dimension to allow the ice crystal sedimentation, so the air parcel dehydration and the representation of the cloud on the longer term simulation, and also adding a very crude representation of horizontal mixing to avoid to have just a curtain of separated columns in our representation. So before talking in more details about our model, let me introduce a bit these superpressure balloons observations. So in our work, we used the STRATEOL2 observations. STRATEOL2 is a French-American project that aims at launching 50 long-duration superpressure balloons during 3 different campaigns. These balloons are to study climate processes in the tropics, and especially the interactions between the troposphere and the stratosphere. 2 types of balloons were created with an equilibrium altitude of around 18 and around 20 kilometers. But I won't distinguish them as they don't show any differences in our results. So as you can see on these maps of trajectories corresponding to the 2 first campaigns of TTL2, the balloons were launched from Mahé in the Seychelles here, and they flew in the tropical bands 2 to 3 months. The specificity of these balloons that we're using here is that once at their equilibrium level, they can follow horizontally the airflow for several months. So they are quasi-Lagrangian tracers, and they can give an insight of the gravity wave activity in an intrinsic frame. More precisely, we have access to observations of the whole spectrum of gravity waves thanks to the TSEN instrument that is notably recording the pressure at a time resolution of 30 seconds. So if I detail a bit more how we get time series of temperature variability from the gravity waves from these observations of the balloons, we first link the pressure measurement to the balloon vertical displacement, and we can also link it to the air parcel vertical displacement. Indeed, as I tried to represent on this little scheme here, you can see, by the way, my mouse, right? On the slides, you can see what I'm showing?
Yes,
Yeah.
but it's rather small.
Oh, I'm sorry. Well, okay, but so on the right, so once they're at their equilibrium level, the volume of the balloons remains constant. Therefore, they are following isopycnic surfaces in red here, when the air parcels follow isentrope surfaces in green here. So we just need to make the transformation between the two with that formula I represented on the second line to have access to the air parcel vertical displacement. And then with an adiabatic gradient, we transform that into a temperature perturbation. So the last step is to filter the signal to only retain the range of frequencies corresponding to the gravity waves. And that is represented by the figure on the right. I'm showing in blue the raw signal that shows the range of frequencies that contribute to the observation, this time series, observed time series. And then in orange is the filtered signal, so only between the two for the frequencies of the gravity waves. So now that we understand better our observations of gravity waves thanks to these balloons, we can talk about the model of microphysics that is using them. So our model is configurable. As you can see on the left in green, we can change its geometry by setting the number of air parcels, their thickness, and their distribution among columns. We can also apply some initial profile of humidity, and finally apply a dynamic scenario with a mean vertical ascent, W bar, that will set the evolution of the background temperature T bar, or also adding the temperature fluctuations from the waves T prime. Then the core of the model is represented in blue. We represent homogeneous nucleation, growth and sedimentation of the ice crystals, as well as horizontal mixing, very simple horizontal mixing that takes into account some wind shear. Very schematically, basically at each time step, the first part of the model is in charge of calculating the ice production in each air parcel, and the second one is in charge of distributing the sedimented ice crystals between the air parcels. And finally, we follow the ice crystals population, looking at their number and their mass in 36 bins of sizes. So this slide is to represent how we have homogeneous nucleation in our model, but I will just sum it up by saying that, as you know, it's very sensitive to the changes in relative humidity and therefore very sensitive to the cooling rates. But on the other hand, I'm going to describe a bit more how we represent the sedimentation, as it's a bit more customized. So we are calculating the sedimentation, making the assumption that the crystals are spherical. So they follow different regimes depending on their Reynolds numbers. And we also make the assumption that the ice crystals are distributed homogeneously in each one of the air parcels. And therefore, the fraction of crystals leaving the air parcel, so sedimenting, is the ratio between the crystal drop distance, depending on their size, and the width of the air parcel. But such a sedimentation only shifts a fraction of crystals from one air parcel to the one just below. So we decided to add some very simplified horizontal mixing that takes into account a wind shear. The principle is that the wind shear will create some relative displacement between two consecutive air layers. So for example, it's the little d on the slide here. And we decide to randomly mix the sedimented ice crystals between two consecutive air layers when this little d is bigger than the half of the length of one air parcel, which is L on my slide here. The first step was to validate our model. So we decided to compare our ice production as a function of the vertical velocity, so for us W bar, without taking into account the sedimentation, to the box model of Spichtinger and Kramer 2013. So when we compare the two figures, we can see that we have the same order of magnitude of crystals, a bit more, but we thought that this tends to validate the macrophysics that we represent here. So we ran many simulations, two main ones that had the same geometry with and without the waves to assess the impact of the waves on the ice crystal population and the air parcel dehydration. But we also looked at the sensitivity of our results to different parameters. For example, the horizontal mixing, the correlation of the wave perturbations in the whole domain, or the amplitude of the waves. I won't describe in detail all these simulations. I will describe in detail only the two main ones, with and without the waves. And then I will move on to more statistical results that use more simulations. The only two things we need to remember is first, that all the simulations had the same geometry of 420 air parcels distributed among 6 columns with a 15 meters of thickness. And they were all lifted with a mean ascent W bar of 0.5 millimeters per second, which is typical of a large-scale background ascent. And the second thing we need to remember is that except for the simulation that tests the correlation of the perturbations in the domain, all the simulations that take into account the waves basically randomly pick samples of the observed time series of these temperature perturbations for each one of the air parcels. And so that tends to maximize the effect of the gravity waves by adding even more randomness in these perturbations. Okay, so now that we have our set of simulations, let's start by looking at what they consist of. So our air parcels follow this temperature profile, so the middle panel on this slide, this one. So this temperature profile that is from radiosonde measurements in the tropical band from Karcher and Podlagen 2019. The domain that we represent is more than 1 kilometer thick, as represented by the vertical blue bar here. it's crossing the call point. And during the 72 hours of simulation, it is lifted by around 100 meters. So here. In the simulation without the waves, the generated cooling rates are very small, of around 4 millikelvins per hour. And we can explain that by the very slow ascent and a domain that is close to the call point. But then when we add the waves, the perturbations from the waves completely dominate the evolution of the background temperature, as you can see on the figure on the left here. Now, so this is now a time series, so temperature as a function of time. You can see that now the evolution of the background temperature is almost a straight line compared to the perturbations of the waves. So that will generate cooling rates that up to 1,000 times bigger than without the waves. And the last thing I wanted to say about this figure is, so for the time series of the temperature perturbations, I've plotted the time series for 2 different air parcels. And as you can see, the perturbations of the waves are different. And that is just to illustrate that we picked randomly the different samples of these observed time series for each one of the air parcels. Okay, so now we can look into more details at the evolution of the ice mass in the domain. So I'm showing on this slide the evolution for the simulation without the waves on the left and with the waves on the right. And I'm just mentioning that the 2 color bars have different scales that I've highlighted in red. So when we look at the evolution of ice mass for the simulation without the waves, we can clearly see 3 different nucleation events. All are occurring below the call point, and they are showing some dependency of the ice mass with altitude. That can be partially explained by the evolution of the gradient of temperature with altitude. When we are too close to the call point, the gradient is too weak and barely triggers any ice. And that also explains the fact that we have smaller ice crystals in the higher levels that will be advected with the air parcels. Now, if we look at the evolution of the ice mass for the simulation with the waves, so on the right, the striking feature of this figure is the numerous nucleation events happening everywhere in the domain, so even above the call point. These nucleation events will create different crystals with various sizes, as expressed by the fit of the ice crystal sedimentation for specific sizes in black lines on my graph here. And so we can see that bigger crystals are created in the upper part of the domain. So they are not coming from the growth of the sedimentation. And smaller ones are staying in the nucleating layer and are advected with the air parcel. So really, this figure is showing the effect of the differential sedimentation that tends to broaden the cloud layer even below the nucleating layer. And overall, we have a very thick cloud layer with a pretty heterogeneous structure. Then we can move on to the evolution of the ice crystals population for the 2 simulations with respect to time on the left and with respect to altitude on the right. Without the waves, we can see that the bins of bigger sizes are only filled for the lower altitudes, when the bins of smaller sizes are filled at all nucleating levels. So we can explain that very well by the sedimentation of the ice crystals. And so we can see that without the waves, we clearly have a dependence of the crystal sizes with the altitude. Then if we look at the evolution of the population in time, we can see the different events of nucleation with the increase of ice mass, as well as the growth of the crystals, for example, that are represented with this little arrow here. Overall, without the waves, we find a pretty narrow population of ice crystals, as described by Jensen et al. In 2010, who described the evolution of ice crystals nucleating and growing pretty much at the same time. Then, when we add the waves, when we look at the figure with respect to altitude on the right, we can see that we don't see a dependence of the size with altitude anymore. The main pattern on the figure is now the sedimentation of the crystals by how they're falling and growing at the same time. And this sedimentation pattern is more clear for the crystals that are more than 3 microns, pretty much. The second thing we can see on this figure is the difference of behavior regarding the temperature perturbations from the waves, depending on the crystal sizes. Smaller crystals will appear and disappear, so they will be more sensitive to these perturbations, as you can see for the smaller beans of smaller sizes. And the bigger crystals will be less sensitive to these perturbations and will be more stable. Then the time evolution of the population is showing clearly the growth of the crystals with these stripes of warmer colors. And this growth is actually slower than without the gravity waves. And we can explain that by the fact that we have perturbations of temperature in a non-saturated environment. So the warmer fluctuations will force the crystals to release some water vapor, and so the whole growth will be slower. So that's for the evolution of the ice crystals population. So after this very descriptive part, I am summing up the results regarding the ice production thanks to this histogram. So it is showing it for the different beans of sizes, for the simulation with the waves in blue, without the waves in black, and with the waves but without the horizontal mixing in red. So as you can see, with the waves, the production of ice is enhanced of 4 orders of magnitude. The waves also have broadened the population of ice crystals, but only towards the smaller sizes, and the bigger sizes are not represented anymore. And we can explain that by the fact that these very high cooling rates from the gravity waves will generate a lot of smaller ice crystals that will capture all the humidity, and so there won't be enough humidity for further growth of the crystals. And finally, we can see that the horizontal mixing was only a secondary effect that would only shift the population of ice crystals towards the smaller sizes. The second thing we wanted to look at was the dehydration of the air parcel. So I'm showing it on the right of this slide, right part of this slide, only for the simulation taking into account the waves, because without the waves, it was too small. It's close to 0 and it wouldn't appear on this graph. So it is the dehydration with respect to altitude, with the mean, the first quartile, and the third quartile. So we can see that the mean effect of the waves is to dehydrate the air parcels of around 5%. But this dehydration becomes more systematic above the cold point, where it reaches around 20%. So that might be a clue to say that the last event of dehydration of the air parcels might actually occur above the cold point. One last result I wanted to describe was the sensitivity of our results to the amplitude of the waves. So in our observed time series of temperature fluctuations, the standard deviation was around 1.5 Kelvin. But as I said, we were taking different samples for each air parcel. The standard deviation was varying a tiny bit between the samples. So we decided to look at the sensitivity to this parameter and to the amplitude of the waves. So we fixed a standard deviation for all of the air parcels with sigma equal 0.5 Kelvin, 1.5 Kelvin, or 3 kelvins. So you have on the right part of the slide the 3 different distributions of cooling rates corresponding to these 3 amplitudes. And then on the left part of the slide, you have just an example of how changing the amplitude is impacting one time series of temperature fluctuation. So if we look at the ice production, when we are varying the amplitude of the waves, we can see that, as expected, having a bigger amplitude is increasing the ice production, and it is also decreasing the mean radius of the crystals. And reversely, having a smaller amplitude is decreasing the ice production, but we have bigger crystals generated. But I guess what we found interesting was that first, it seemed that the ice production was very sensitive to this amplitude, as it is increased by several levels of magnitude between the 0.5 and 3 kelvins. But the mean radius wasn't changing much, only maybe doubled, but not more. And the second thing that was interesting was to see that only 0.5 kelvins of standard deviation was enough to trigger the nucleation of ice. Finally, I just want to say that, as you can see, the maximum size for the simulation with only 0.5 Kelvin of amplitude, the maximum size is smaller than for the other simulations. But this, in this simulation, there were only a few events of nucleation triggered, and I didn't run enough simulations to have a decent statistical robustness. So this is only coming from basically the details of the simulations. The last step of our work was to compare our ice production to actual observations. So we chose the NASA Airborne Tropical Tropopole Experiment, so ATREX, that gives in situ observation. So from, for example, the campaign in 2014 over the Pacific in the TTL. We first looked at the ice crystal density. I'm showing it on this graph for the simulation without the waves in black and with the waves in blue with the circles. As you can see, without the waves, the ice production is not realistic, it's too low. But when we add the waves, we have ice production that is closer to the observations. One main difference is that we overestimate the highest densities, but we can explain that by the fact that these very high densities are from very fresh nucleation events with very high cooling rates that are hard to observe. But the most interesting feature of this figure is how we are actually fitting pretty well the lower densities between 10 and 100 crystals per liter. And that is interesting because usually these lower densities are explained by the presence of heterogeneous nucleation when we achieved to have them with only homogeneous nucleation. Then we looked at ice crystal population. So I'm just representing it here for the simulation with the waves, as without the waves, it was too unrealistic. We can see that we are in the range of the observed sizes. We are overestimating the smaller crystals, but we can explain that by the fact that the instrument was limited for the crystals up to 1 micron. And we are completely missing the bigger ones. And one of the reasons for that is that our domain is limited in altitude. And so the growth from the sedimentation is also limited. Then I'm showing again these figures, but adding more curves on them because I just want to show the impact again of the waves amplitude. So if we look on the left at the sky blue curve that corresponds to the simulation where we fixed the standard deviation to 1.5 Kelvin, we can see that we're fitting even better the observations. We have increased the occurrence of lower densities, and we have decreased the occurrence of very high densities. We can explain that by the fact that in the simulation with just the time series of the waves, these very high densities of ice crystals were from a few nucleation events with very high cooling rates. And so fixing the standard deviation to 1.5 Kelvin is eliminating these few events. Then when we lower the amplitude to 0.5 Kelvin, so it's the very dark blue curve, we can see there that we're fitting pretty well, the 2DS instrument. But that is, I guess, not a very good thing, because the 2DS instrument was limited to observe the very smaller ice crystals, so with a radius smaller than 0.5 micron, I think. And these crystals are usually responsible for these higher densities. So this fit is not really to take into account. And then when we increase the amplitude to 3 kelvins, we can see that we are completely overestimating the highest densities, but we're fitting pretty well the 2DS for the lower densities. And finally, if I compare again with the ice crystals population that are observed, we are staying in the same range. And this figure is just showing what we said previously, that increasing the amplitude is just increasing the ice production more, that it really impacts the mean radius of the population. So to conclude, I've presented some results from our simplified 1.5 dimension model that could be combined with superpressure balloon observations. This led to a paper that is in ACP. We found that waves were triggering more ice crystals even above the cold point, and they were creating a wider population of ice crystals, especially towards the smaller sizes, but they were preventing the bigger ones from appearing. And then we found that the waves were responsible for up to 20% of dehydration of air parcels above the cold point. If we want to go a bit further, we found that our way to maximize the effect of the waves was generating a very thick cloud structure that was very heterogeneous. And that is far from the observations that we have of these clouds at these altitudes. So for example, I'm showing on this slide a profile from an instrument that we were carrying on the balloons, a backscattered LiDAR, and that gives us very nice profiles of the cirrus. And we can see that these profiles are very, narrow when we had a very fixed structure. So we think that if we were running our simulations on longer time, we might achieve these narrower structures. And finally, we looked at the sensitivity of our results to the wave's amplitude. And as we saw, increasing the amplitude was increasing the ice production. But when we were decreasing the amplitude, the results were more sensitive to the simulation details. So I would like to continue to work on that model. Especially, I would like to look at the effect of larger scale waves on the ice production. And we have pretty good observations of STRATEOL2 for that as well. And we also would like to combine observations from different instruments from STRATEOL2. And for example, we found a good study case, or we hope it's good, but interesting study case where one of our instruments really pictured a nice gravity wave so we can get their characteristics. And another one, so the backscatter LiDAR has a very nice cirrus profile to give us. So we want to look at that as well. Thank you for your attention.
Thank you, Milena.